you have an array, you're going to divide that into two halves. We have two halves of the array. And what we're going to do is you're going to sort the sub-arrays, these two smaller arrays. And then use the solutions, means use the two sorted arrays to sort the bigger array. Okay? So in general, we are going to divide a problem into several sub-problems. We'll see merge sort right after this. Okay? But in general, in divide and conquer, what we'll do is we'll divide a problem into several sub-problems. In the case of merge sort, to two sub-problems. We are going to solve the sub-problems and use the solution of the sub-problems to solve the larger problem. Okay? While after we sort the two sub-arrays, we can find this, we can sort the overall array. Just an example. Let's say you have something like this. Right? So initially it will be what? 14, 5 and 3, and this is what it is, right? I just split them into equal halves. And then if I sort this becomes what? 3, 5, 14, right? I go through a sorting process for that subarray, and then a sorting process for this. Then how do I merge it? I take up this element, the leftmost element here, and compare with this leftmost element here, 3 and 6, which is greater? 6. So which is less? 3, right? So 3 is less, so then I move my index to the, so I compare these two, and 3 was less, so I move now my pointer to the next element here, and compare 5 and 6, which is again smaller, 5. So 5 is smaller, and then my pointer is over here. So now I compare 14 and 6, which is smaller, 6. So now 6 is here, so I have to move the pointer here, 7. So compare 14 with 7, which is smaller, 7. And then 8 and 14, 8 is smaller, so you're done with this array. So when you're done with one array, the rest can be just put like that, but here also you have only one element left over, so you can put that left over element there. So now this is the sorted portion, the sorted final array. Okay? So we'll do that recursively, which means we won't, like initially I said we will sort this, right? Initially we just split it into 14, 5 and 3, and this is 6, 8 and 7, isn't it? So how to solve this? Let's just apply the same thing recursively all the way when it goes to 1. So let me show you how it works. We can come back to this. You see here, this is the array I have. So I just split it into two halves, 8, 3, 2, 9, 7, 1, 5, 4. How I sort these two arrays? I again break them. So I break 8, 3, 2, 9 to 8, 3 and 2, 9. And then 7, 1, 5, 4 to 7, 1 and 5, 4. And again, how I sort 8, 3, I break it down all the way to one array, one element array. So 8 and 3, then 2 and 9, 7 and 1, and so on. Now I compare really, 8 is sorted by itself because it's the only element array. 3 is also sorted by itself. Then I do my comparison like what I did. I compare 8 and 3. 3 is the smaller one, so it gets here, and 8 is the next last smaller one. So 3 and 8 are now sorted. Similarly, 2 and 9, 1 and 7, 4 and 5. So now you merge these two sorted arrays to a sorted array. So I compare 3 with 2, 2 is smaller, then 3 with 9, 3 is smaller, then 8 with 9, right? Like how we did there. Similarly, I merge these two, then I merge these two. So this is a good example for recursion, as we'll see in the pseudocode later. Okay? You recursively call, break the bigger array to smaller array all the way to size 1 and then merge. So as you see in this case, you are first dividing the problem into sub-problems, solving the sub-problem, and then merging the solutions of the sub-problems to find the solution for the larger problem. The solution for sub-problems is sorted, smaller sorted arrays. We are merging them to solve the larger array. Okay? So that's the principle of divide and conquer. how do we do that in general? So there's a theorem. You have something to ask?
Yes, I do. Is the class more based on the problem-solving strategy?
Yes.
So is this like, is it just me or is it just mathematics or programming? Because the summations, they're for loops. So we're just looking at the most integral case and trying to think in terms of code. We're thinking pseudocode and math versus
Yes,
thinking
a
of...
combination of the two actually. So the problem-solving skills, and then analyzing the pseudocode or the algorithm, the problem, the idea behind the solution, right? Like insertion, sort, or all these things. So analyzing the time complexity, how long it takes to do that. So you use a pseudocode approach to that. And then you do the actual math, do all the summation to analyze the time complexity theoretically and say what it is. Okay?
Okay.
So given a problem, you are basically designing the solution for the problem using the different strategies. So you saw brute force, right? The string matching. Then we saw one case for decrease and convert. You should have seen several other examples in your data structures course for each of this. But even then, if you don't remember, still you're looking at here as a strategy. Insertion sort is a strategy for decrease and convert. Merge sort is a very good strategy for divide and conquer. Solving a larger problem by dividing into smaller problems, and then solve smaller problems to obtain a solution for a larger problem. Then we say greedy strategy. Next, dynamic programming. So looking at more from a problem-solving strategies. Okay. So given any problem, you should be able to think about what strategy I would apply, rather than trying to solve it by just trying different ways. Just each problem by itself will have inherent nature. Okay, it can be best solved by divide and conquer. It can be best solved by dynamic programming or greedy or different strategies. So throughout this course, you are going to develop the skill of identifying what strategy we need to use to solve a given problem. Okay. Of course, sorting can be done through different strategies. That's what we have been saying. Insertion sort is one idea, using the decrease and convert. Merge sort is another strategy. Of course, each strategy will have its own pros and cons. We'll see the time complexity may vary. Insertion sort pretty much we add that of n squared. Decrease merge sort will have that of n log n, so it's more efficient. Of course, there are some trade-offs, which we'll also see. Okay? So clear?
That's clear.
Alright, so let's look at this theorem called master theorem. You might have seen this before. Have you heard of this? Master theorem? Alright, so in the first module, we solved recurrence relations through the kind of hardcore approach, right? Given a recurrence relation, what we did, we kind of did induction-based approach, right? Remember, we solved something like x of n as x of n minus 1 plus 1, or n, what we did. We just substituted for x of n minus 1 again on this, and then got x of n as x of n minus 2 plus something, and then we generalized it to an I term, and then we had a basic condition to which we reduced. That's what we did in the previous module, if you remember, right? So now we are going to look at a theorem that can also help us to solve recurrence relations. So from now on, I'll explicitly specify. If I want to solve using this master theorem, I'll say, after giving the recurrence, I'll say use master theorem. If I don't say, it's up to you to choose one of the two. But if I want you to solve using typically the n equals 2 to the k approach, remember we did some examples like this by choosing n equals 2 to the k. If I ask you to do that, then you have to use that approach. Okay? Right? Okay, so for now we'll focus on this master theorem. So you need to kind of remember the rules or kind of as a small formula. But if you do a couple of problems, you should be able to remember it more easily. So practice, that's the key thing here. Okay? So the idea is we are having a problem of size n, and we are dividing into several problems of size n over b. So we have a problem of size n, and we are breaking that into several sub-problems. Each sub-problem is of size n over b. So we're having a 100 element array, we can break it into an array of size, say 5 elements, right? So each of this is an array of size 5 elements and so on like that. And we solve A of the sub-problems, because we have several sub-problems here, right? We'll solve A of those sub-problems, right? And then merge the solutions of those sub-problems. visualize that. We're breaking a problem into several sub-problems, each of size n over b. And then you are merging, solving A of them, and then merging the solutions of those problems. I may have a figure here. Like as I showed here, we have only two problems here, but in general, n over, each problem is of size n over b. And here you're solving both the problems. In general, you may have several sub-problems of size n over b, each of size n over b. We are solving A of them, need not be all of them. Okay? In general, you could solve, in worst case, all of them, but you're solving A of them. So let's say these are three problems you're solving. So A equals 3, right? So since you're solving only A of these problems, you'll have only A solutions. So you're going to merge all those solutions from A of the sub-problems and get the solution for the larger problem. Okay? So the way to look at this is the overall time complexity to solve the problem of size n is the time complexity to solve a particular problem of size n over b, and then you're going to solve A of those problems, right? So A times t of n over b is the time to solve all those A sub-problems. Each sub-problem is of size n over b. So to solve one particular sub-problem is going to take this time. We are going to solve A of them, that's why it is A times t of n over b. And you are just solving the sub-problems, and this is the time complexity. Then you have to merge the solutions like we did for merge sub, right? So this is the time complexity to combine the solutions of the sub-problems and get a solution for the larger problem. Okay? So you see this diagram has two components in it. The first component is the time taken to solve the sub-problems. You're going to solve A sub-problems, and each sub-problem is of size n over b. So this is the time to solve the individual sub-problems. And then you're going to merge or combine the solutions of the sub-problems and get a solution of the larger problem. So like we did the comparison and you merge the two sorted subarrays to get a larger subarray, we need to spend some time to do comparison and stuff like that. So that is captured in this f of n. Okay? To combine the solutions, we need to spend some time. Right? Is that clear? So we'll see sometimes both terms may be dominating. The sub-problems may be dominating the solutions to the time taken to solve sub-problems. Sometimes the time taken to combine the solutions may be dominating. Sometimes both may be dominating. So we'll work out several examples. So I'm just telling the theory initially. Okay? So this f of n, the time to combine the solutions, can be represented as a polynomial of theta of n raised to d. So this f of n can be represented as theta n raised to d. Right? So typically you will have something like what? T of n so try to understand as much as you can as I explained when you work the examples, things will be very clear. Okay? So this will be the kind of form of problems we'll see. A times t of n over b plus theta of n raised to d. Like we have 4 times t of n over 2 plus n. N is n raised to 1, right? So those kind of expressions. So we have what here? 3 values. A, B, and D. So your first job is, given the recurrence like this, compute B raised to D. B raised to D. And compare that with your A. Okay? So you have A, B, D. Find B raised to D. Compare with A. The formula is given there. If A is less than B raised to D, then T of n is, as I stated there, if A is less than B raised to D. So what does it really mean? You can say B raised to D is the most dominating term compared to this one. So it means D is the more dominating. Where is D here? D is here, the time to combine the solutions. Right? So this D is more dominating. So if A is less than B raised to D, we can say T of n is simply theta of n raised to D. Right?
Where does Is it me, or where does the D come from? Does D come from
D is the exponent.
Oh, the exponent. So why would it be exponential? Are you
Not
multiplying?
exponential. Like here, if you have n here, this is n to the 1, n squared means d is 2, n cubed means d is 3.
Oh, sorry, I meant power function.
Power.
But so the D would be multiplied n times b, n times b, n times b. Is that where the D comes from? How many times?
No. This is b, right?
Right.
So b, n over b is the size of the subproblem. So if you have a problem of size 100, you're breaking into, say, 5, array of size 5, then n over b is 5.
Okay.
Okay? So when we work out the examples, will be more clear.
Okay.
So just hold on for time. So if A is equal to B raised to D, then the formula is T of n is theta of. So here, what we mean by A is equal to B raised to D means both these terms are dominating. This term is dominating as well as this term is dominating. So in the expression for the time complexity, it will be theta of n raised to D log n. Okay, so this is the formula. You can prove this. We are not proving it in this course. Just take it as a formula. Okay, and the last thing is A greater than B raised to D. If A is greater than B raised to D, then T of n is. You see here, if A is greater than B raised to D, then D term is not dominating, which means the combining part is not dominating. The solutions to subproblems, the time taken to solve the subproblems is more dominating. So then we can say it is theta of n log a to the base b. There is no d term in the final time complexity. You see here, this is simply n raised to log a to the base b. There is no d term here. Right? So if a is greater than b raised to d, there is no d term in the final expression. It is theta of simply n raised to log a to the base b. Okay? So we have to remember these three as formula, depending on which case, A and B raised to D. So depending on the appropriate value, you have to use the appropriate formula. Okay? So let's do some problems. Let's take up the first regression I have there. What I have there, T of n is 4 times T of n over 2 plus n. So we are breaking some problem of size n to n over 2 subproblem. Each subproblem is of size n over 2. There may be some overlapping, right? Possible. Like you see here, if you're breaking a problem of size n into problems of size n over 2, we have actually only 2 subproblems. But you see here, you solve 4 of this subproblem, which means when you break it up, depending on the problem, there may be some overlap between the different problems, right? So we are solving 4 such subproblems and combining those solutions, and then this is the time complexity to combine the solutions. So we want to solve this recursion. That's what we are now interested at. T of n is 4 times T of n over 2 plus n. So how do we approach solving this? Given a recurrence like this, your first step is to find A, B, B. What is A? 4. B?
2.
2. What is B?
1.
Why 1? Because n can be written as n raised to 1. So D is 1. So after you locate your A, B and D, find B raised to D. B raised to D is 2 to the 1, right? Because B is what? 2, D is 1. So A is 4, B is 2, D is 1. So B raised to D is 2 raised to 1, which is 2. So compare your A and B raised to D. Which is greater? A, right? A is greater than B raised to D because A is 4, B raised to D is 2. So which formula should apply? The A term is dominating, which means between the two, what is our recurrence? Recurrence in general is this, right? A times T of n over B plus theta n raised to D. So here you see A is greater than B raised to D, which means the D term where you combine the solutions is not dominating. This is what is more dominating. So the final formula for the time complexity is that one that I just wrote without involving the D term. So it is this formula. N raised to log A to the base B. This is having D in it. Right? So this is theta exponent, I can bring it to the thing and say log 2 to the base 2. Okay? So log 2 to the base 2 is what?
One.
The number and the base are the same, it is 1. Okay? That's why it is 2. Right? If I have log 8 to the base 2, what is that? Log 8 to the base 2 is
3.
y.
That is 2
2
cubed.
cubed to the base 2, so it is 3 times log 2 to the base 2, which is 3. Okay, so you should be clear on that. Okay, so we have now theta of n squared. Right? So let's do step by step. So let's do the second one. What is your A, B, D for second? 4t NO2 plus n squared. A is 4, B is 2. Right? We have t of n is 4 times t of n over 2 plus n squared. So what is A, B, D? A is
4. That's 2.
So what's the next step? Find what? You got A, B, and D. So what's the next step? Find B O rise to D. So what is B rise to D in this case? 2 rise to 2, which is 4. So then what you should do? Compare A and B rise to D. What are they here? Equal. So if A is equal to B rise to D, what is your formula for the time complexity? T of n is
In power D.
n rise to D log n. So this is where both parts of the equation are dominating. So what is your D here? 2. So it's n squared log n. So this is your final solution. Okay? So let's do n cube. If t of n is same thing, I'm just increasing the complexity on the left, on the second combining step. Okay? So now what is your A, B, D? A is still 4, B is, D is 3. Now anyone here tell me what's the first step to do? B raised to D. So it is this. So now compare A and B raised to D. So which is greater? B raised to D is greater, right? A is less than B raised to D. A is 4, B raised to D is 8. So the D term is dominating. So time complexity is simply T of n is n rise to D. So it is n rise to 3 n cube. Right? So if you notice, the only thing I changed in these three problems is from n you have n squared, you have n cubed. And the time complexity increases corresponding. You have T of n was initially theta of n squared, and then n squared log n, slightly more than n squared, and then n cubed. Right? So as you increase the time to combine the solutions, this part was the same. As you increase the time to combine the solutions from n to n squared to n cubed, or theta of n squared, theta of n cubed, like that, the time complexity, the overall time complexity increased from T of n is theta of n squared, T of n is n squared log n, and this is n cubed. Right? Okay? You see, as we increase this from n squared, n cubed, it increases from n squared log n, n cubed. Let's do the last one. What's the last one we have? T of n is 2t n over 2 plus 1, right? You have a 1 here. You don't have n, but you have something like 1. So what can you do for the d? You have to get somehow this in the format of theta of n raised to d. What can I do to 1 so that I can get it in this format?
1 times n to the power of 0.
1 is nothing but n raised to 0. Anything raised to 0 is 1, right? So I can write my 1 as theta of n raised to 0. Okay? So the same 1 I can write it as what? Theta of n raised to 0. Right? So my d is n raised to d. So n raised to 0. So what is your d here? 0. So I can write my d as 0. So now what is your next one? b raised to d is 2 raised to 0. What is that? So then compare a and b raised to d. So a is 2, b raised to d is 1. So which is greater? A. So what is your final answer? T of n is when a is greater than b raised to d. It is theta of what? N raised to the numerator, n raised to log a to the base b. Okay? If a is greater than b raised to d, it is n raised to log a to the base b. So what is that? Theta of n raised to log a is what? 2. And what is b? b is also 2. So log 2 to the base 2 is 1. Log 2 to the base 2 is 1. So overall it is what? n raised to 1. Log 2 to the base 2 is 1. So it is n raised to 1. And what is that? Theta of n. Okay? Theta of n. Clear? So if you practice problems, you will get this. I have some more. 3, so I tried it, so let's see how you have to do this. So we have 3 times. So this is a sure question in the quiz or exam, so you know how to do this.